Always up for a challenge. What do we got?
Well, buckle up because we're going deep into the realm of antimatter and entanglement.
Ooh, getting quantum. Love it.
Yeah, and a huge thanks to all of you who sent in this awesome research. Some truly wild stuff. We're going to try and untangle all of it. You know, it's funny. When I hear the word antimatter, I still get Star Trek vibes.
Haha, yeah. But it is actually real, not just sci-fi.
So before we go too far, let's make sure everyone's on the same page. What exactly is antimatter?
Okay, so imagine like mirror image of the particles that make up everything we know and love.
Okay, I'm picturing it.
So for every particle, there's a corresponding antiparticle.
So like an evil twin.
Haha, sort of. But instead of evil, think opposite charge.
Opposite charge, so same mass, different charge.
Exactly. So for instance, an electron with its negative charge, its antiparticle, is a positron with a positive charge.
Okay, so they're like perfectly balanced, but opposite.
Yeah, perfectly balanced as all things should be.
Thanos would be pleased. But seriously, what happens if these matter and antimatter particles actually meet?
Well, let's just say they don't exactly get along. They can't exist in the same space. When they come into contact, they annihilate each other. Poof, gone.
So like a cosmic explosion.
In a way, yeah. They release a burst of energy. All that mass converts into pure energy. E equals mc squared and all that.
Wow. Okay, so that's antimatter. Now, entanglement, this one really messes with my head.
Yeah, it's definitely one of the weirder aspects of quantum mechanics.
Okay, so how could two particles separated by, like, light years instantly affect each other?
It's almost like they're linked by some invisible thread, but instead of a thread, it's more like their fates are intertwined. You measure the state of one particle and boom, you instantly know the state of the other one.
So are we talking faster than the speed of light here?
It seems that way, doesn't it? It's one of the big mysteries of quantum entanglement.
Einstein called it spooky action at a distance.
He wasn't a fan of the idea. It really challenged his view of how the universe should work.
But this spooky action is real, right?
Oh yeah, experimentally confirmed. This correlation between entangled particles is stronger than anything classical physics can explain.
Wow, okay, so we've got these two crazy ideas. Antimatter, the mirror image of matter, and entanglement, this spooky connection between particles. Are they related?
That's the big question. And according to the research you've sent, it seems antiparticles can actually be created in entangled states.
Wait, seriously, they can be born entangled?
That's what the research suggests. It's like they're linked from the very moment of their creation.
Okay, give me an example. I need a visual here.
All right, picture a neutral pion. It's a type of subatomic particle. Now imagine it decays. Sometimes it can split into an electron and, you guessed it, its antiparticle, a positron.
Okay, I'm with you.
And get this, sometimes these electron-positron pairs are born entangled.
So they're like quantum twins, forever linked. Does that mean, like, every electron in my body has an entangled positron counterpart out there somewhere?
Whoa, hold on there. Not necessarily. It's not quite that simple. For particles to be entangled, they need to have a shared history. That shared history is what links their fates.
Okay, so a random electron in my hand and a positron, say from a distant supernova explosion, wouldn't be entangled just because they're antiparticles.
Exactly. Just being an antiparticle doesn't automatically mean entanglement. There needs to be that special connection, that quantum handshake in their past.
Okay, I get it. Shared history, not just opposites. But hold on, does every particle actually have an antiparticle? Like, is that a rule of the universe?
Well, the Standard Model of particle physics seems to think so.
Can you remind us what the Standard Model is again?
Think of it like a giant periodic table, but for the fundamental particles and forces in the universe.
Ah, okay, got it.
And this model, it strongly suggests that for every particle, there must be a corresponding antiparticle.
Must. Like, it's a cosmic requirement. What's the logic there?
Well, one of the big reasons is something called the CPT theorem. It stands for charge, parity, and time reversal.
Okay, that's a mouthful. What does that mean?
It basically says the laws of physics should stay the same even if we flip the charge of particles, mirror the universe, and reverse the flow of time.
So, like a triple cosmic backflip.
Haha, yeah, something like that. And this symmetry, the CPT symmetry, it means that if a particle exists, its antiparticle must also exist to keep the universe balanced.
So, no escaping those antimatter twins. But this brings up a big question. If the early universe had almost equal amounts of matter and antimatter, why is our universe dominated by matter today? Shouldn't they have just annihilated each other, leaving nothing but energy?
That's the million-dollar question. The matter-antimatter asymmetry problem, one of the biggest unsolved mysteries in cosmology. Something must have tipped the scales in favor of matter, but what that something is, well, we're still working on that one.
So we've got this cosmic imbalance, this surplus of matter. Fascinating. Okay, we've talked about how particles and antiparticles have opposite charges, but I've heard there's an exception, the photon. Tell me more about that.
Oh, yes, the photon, the particle of light. It's a bit of a rebel. It's its own antiparticle.
How is that even possible?
Well, remember how we said a key characteristic of an antiparticle is its opposite charge? Well, photons have zero electric charge,
Right.
and the opposite of zero is still zero.
So if you try to create an antiphoton by flipping its charge, you end up with the same photon you started with.
You got it. It's like trying to find the opposite of zero. There just isn't one.
Mind blown. It's amazing that light, the very thing that lets us see the universe, plays by these bizarre quantum rules.
It is pretty wild. And the fact that the photon is its own antiparticle, it has some pretty profound implications for our understanding of the universe.
Okay, I'm intrigued. Why is it so significant that the photon is its own antiparticle?
Well, for one thing, it really highlights the importance of symmetry in physics. This self-annihilating nature of the photon actually helps uphold that crucial CPT symmetry we were talking about.
Right, the rule that physics shouldn't change if we flip charges, mirror the universe, and reverse time. But how does the photon, being its own antiparticle, fit into all of that?
Let's break it down. Applying charge conjugation to a photon doesn't change anything because it has no charge to flip.
Right, makes sense.
Now, the parity transformation, that's like creating a mirror image, that does affect the photon.
How so?
It flips the direction of its momentum and its polarization.
Polarization.
Yeah, just the direction its electric field oscillates in.
Got it.
So it's like we're flipping the photon, but it's still fundamentally the same particle. What about time reversal?
Okay, I'm following so far.
Time reversal also flips the photon's momentum and polarization. But again, these are just changes to its state, not its fundamental identity as a photon.
So even after all that flipping and reversing, the photon comes out unscathed, still a photon. CPT symmetry is upheld.
Exactly. It's like the universe is playing by its own set of rules, and the photon fits right in.
This is fascinating stuff, but I want to shift gears back to entangled antiparticles for a moment. You mentioned a pion decaying into an electron and positron, but how does that entanglement actually work? What does it mean for those particles to be linked?
To really understand that, we need to dive into a specific type of entangled state called a Bell state.
Okay, Bell states. What makes them so special?
These Bell states represent, like, the maximum level of entanglement between two particles.
Okay, so max entanglement. Got it.
So imagine we want to measure the spin of our entangled electron and positron.
Spin, that's like a particle's internal rotation, right?
You got it. It's this intrinsic angular momentum that can be either up or down. Now, when these particles are in a Bell state, if you measure the electron's spin and find it's up, you instantly know the positron's spin is down.
Whoa, hold on, instantly. Faster than light. How is that even possible?
That's the beauty and the mystery of entanglement. It's not that the measurement of one particle sends information to the other. It's that their fates are intertwined from the moment they were created. Like they're two sides of the same coin, forever linked.
Okay, I need a minute to process this. So this link, this entanglement, it doesn't just vanish when the particles go their separate ways.
Not necessarily. The entanglement can persist as long as the particles remain isolated. But if they interact with other particles, that entanglement can be lost or transferred.
So it's a delicate connection.
You could say that. And this fragility is one of the big challenges in using entanglement for practical applications.
Yeah, like how do you even begin to harness something so delicate and strange?
It's like trying to capture lightning in a bottle.
Speaking of applications, what are some of the potential real-world uses of entangled antiparticles? Like, why should we care about this stuff?
One of the most promising areas is quantum computing. Imagine computers that are exponentially more powerful than anything we have today.
Quantum computers, I've heard about those. They're supposed to be like the next big thing, right?
They have the potential to revolutionize everything from medicine to materials science, even artificial intelligence.
It's incredible to think that something as bizarre as entangled antiparticles could lead to such groundbreaking technologies. It really shows the power of fundamental research.
It does. You never know where basic research will lead. Who knows what other wonders are waiting to be uncovered as we delve deeper into these mysteries.
It's exciting to think about. Yeah, it's truly mind-blowing. Okay, I gotta ask, what other crazy stuff did we find in all this research?
Well, you mentioned annihilation earlier, and that plays a key role in one of the more fascinating aspects of entangled antiparticles.
Oh, okay, annihilation. Remind me, what happens again?
Remember, when a particle and its antiparticle meet, they can't coexist. They annihilate each other, release a burst of pure energy.
Right, right. Total annihilation. Okay, so how does that tie into entanglement?
We'll get this when entangled pairs, like our electron-positron buddies, when they annihilate each other, the photons, those particles of light, they inherit the entanglement.
Wait, what? Seriously? The entanglement doesn't just disappear?
Nope, it gets passed on to the photons. It's like the spooky action lives on, just in a different form.
It's like a chain reaction of quantum weirdness. I love it. So, just to be clear, we're talking about creating entangled photons from entangled electron-positron pairs.
Exactly. And this is huge. Being able to create entangled photons reliably opens up so many doors in fields like quantum cryptography and quantum communication.
Quantum cryptography, that sounds intense.
It is. It's all about using the principles of quantum mechanics to create super secure communication channels, like unbreakable encryption.
So spies and hackers beware.
Haha, pretty much. And then there's quantum communication, which is all about using entanglement to transmit information, potentially even faster than the speed of light.
Whoa, faster than light communication. That's straight out of science fiction.
It's still early days, but the potential is there, and it all comes back to this amazing connection between antimatter, entanglement, and light.
I'm starting to see how these abstract quantum concepts could really change the world. It's not just theoretical anymore.
It really does bridge the gap between the mind-bending world of quantum mechanics and real-world applications. And, it all underscores this deep connection between different areas of physics. We're talking about antimatter, entanglement, photons, and it's all intertwined.
It's like a cosmic web connecting everything together. Okay, I also want to touch on something we mentioned earlier, the matter-antimatter asymmetry problem. The whole mystery of why the universe is dominated by matter if it all started with equal amounts of matter and antimatter.
Yeah, it's a big one. And to be honest, we don't have all the answers yet. But there are some interesting theories out there.
Okay, hit me with them.
Well, one possibility is that there's like a subtle difference in the behavior of matter and antimatter that we haven't been able to detect yet, like a tiny imperfection in the mirror image.
A crack in the cosmic mirror.
Haha, yeah. Another possibility is that there are processes in the early universe, processes that we don't fully understand yet, that somehow favored the production of matter over antimatter.
So like a cosmic bias towards matter.
Exactly. Something might have tipped the scales.
Man, it's amazing how many questions we have about something that happened billions of years ago. Every answer just seems to lead to more questions.
It's true, but that's what makes science so exciting. It's a never-ending journey of discovery. The more we learn, the more we realize how much we still don't know.
Well said. Okay, before we move on, let's recap entanglement one more time. For our listeners who might be new to this, what's the one thing you want them to take away from all this talk of entanglement?
If I had to sum it up, I'd say that entanglement shows us that the universe is way stranger and more interconnected than we could ever imagine. Like, reality itself is just way weirder than we think.
I think that's a great way to put it. It's a reminder to stay humble, to stay curious, and to never stop questioning the world around us. Yeah, it really is humbling to think about how much we still don't know.
It is. It's a good reminder that we're still just scratching the surface.
Okay, so speaking of things we don't know, I have a question about something we talked about earlier.
Okay, shoot.
You mentioned that the photon is its own antiparticle.
Right, our little rebel particle.
Yeah, it's mind-blowing on its own, but here's where I'm going with this. We've been talking about the matter-antimatter asymmetry problem. That whole mystery of why the universe is dominated by matter.
Yeah, one of the biggest mysteries out there.
So if the photon is its own antiparticle, does that mean light itself is somehow neutral in this cosmic battle between matter and antimatter?
That's a great question, and to be honest, it's one that scientists are still debating.
So no definitive answer yet.
Not yet, but it's a fascinating area of research. Some scientists speculate that because photons are their own antiparticles, they might not have participated in the same way as other particles in those early universe annihilation events.
So while matter and antimatter were busy walking each other out, light was off doing its own thing, playing by a different set of rules.
Possibly. And if that's true, it could change how we think about the evolution of the universe and why we see this matter-antimatter imbalance today.
It's amazing to think that something as seemingly simple as light could hold the key to such a huge mystery.
It is. It just goes to show that we need to keep an open mind and explore every angle.
This whole deep dive has really given me a new perspective on the universe.
Me too. It's incredible how it's all connected.
Yeah, we started with antimatter, explored entanglement, and ended up talking about the nature of light itself. What a journey.
And hopefully it's inspired you all to keep learning and exploring the universe.
Absolutely. To everyone listening, keep that curiosity burning. Don't be afraid to ask those big, weird questions.
You never know what amazing discoveries are waiting to be made.
Well said. This deep dive has been a perfect example of that. So many answers, but even more questions.
It's a good reminder that learning is a lifelong journey.
And what a journey it is. So until next time, keep exploring, keep questioning, and keep that sense of wonder alive.